Greetings, my dear listeners. Today, we are setting out together on one of the most mysterious journeys of modern science. Imagine this. In the silent depths of space, among billions of stars, there exist objects that break every familiar law. Black holes. They are like yawning portals into which light, matter, energy, and, most importantly, information can vanish. What happens to information when it crosses the point of no return, the event horizon? This question has tormented scientists for decades. It unites physics, philosophy, and, in a sense, even art. For it is not only about the cosmos, but about the very laws by which reality is woven. Imagine holding a book in your hands. Let's say it's a novel by Tolstoy. You know that every letter, every line carries meaning. Now picture yourself throwing this book into a black hole. The material substance of the book disappears for an outside observer. But where does the text itself go? Where do Tolstoy's thoughts, encrypted in the combination of letters, vanish? This metaphor represents the central paradox that Stephen Hawking, John Preskill, Leonard Susskind, and many other great physicists of our time wrestled with. According to the laws of quantum mechanics, information cannot simply vanish without a trace. Yet, according to the laws of general relativity, a black hole seems to promise the opposite. And here lies one of the greatest conflicts of modern science. But before diving into the problem itself, let us briefly step back into history. In the 18th century, Isaac Newton already understood that gravity could be so strong that even light might not escape a massive body. His follower, the French scientist Pierre-Simon Laplace, even dared to suggest the idea of dark stars, invisible to the eye. At the time, this sounded more like philosophical speculation than strict physics. Yet the seed of the idea had been planted. Then came the 20th century. Albert Einstein gave the world the general theory of relativity, a brilliant equation describing space and time as a flexible fabric. Shortly afterward, the German astronomer Karl Schwarzschild, while serving on the front lines of World War I, solved Einstein's equations for a spherically symmetric mass. His solution became what we now call a black hole. Remarkably, a man in the trenches, surrounded by the thunder of cannons, created a formula that opened a window into the abyss. Even Einstein himself was initially skeptical of these ideas. Black holes seemed too exotic, too unreal. But nature proved bolder than theorists. In the mid-20th century, astronomers began discovering quasars, sources of immense energy that could only be explained by the presence of supermassive black holes. Gradually, the doubts faded. Black holes became part of astronomical reality. Now let us return to our central question. What about information? Physics is not only about stars and masses, but also about describing the world itself. Information is a fundamental category, just like energy. It is encoded in everything, in the arrangement of atoms, in the quantum states of particles, in the patterns of light. If information can disappear, then one of science's cornerstones, the principle of conservation, collapses. Picture a vast library with millions of books. Each volume represents a state of the universe. And one day, you take a book and throw it into the fire. The paper burns, the ink disappears. Yet if we are absolutely honest, we must admit, the information is not destroyed, only transformed. In the ashes, in the heat, in the smoke rising into the air, there still lingers a trace of the original text. If we had an infinitely precise instrument, we could reconstruct it letter by letter. This is the principle quantum mechanics holds to. and black holes seem to defy it. Stephen Hawking boldly proposed that black holes evaporate, emitting what is now called Hawking radiation. But this radiation is completely random. It carries no information about what fell into the black hole. Hawking claimed, "Information is lost." This declaration challenged the entire scientific community. His debate with John Preskill and Leonard Susskind became legendary, an intellectual duel where the fate of physical law itself was at stake. Doesn't this echo ancient philosophical disputes? When Socrates asked questions that had no easy answers, or when Plato argued about the nature of ideas. Here, too, the struggle is not merely for a formula, but for the very understanding of how reality works. Can reality forget? Can the universe be without memory? I invite you to pause and reflect. What does memory mean to us? Not only in science, but in human life. Is it not information that defines who we are? Our memories, our stories, even this very podcast. All of it is information, packaged into words, sounds, and symbols. If information can vanish, does a part of ourself vanish with it? This is why the question of information in black holes resonates not only with theoretical physicists, but also with philosophers, poets, and I dare say, each of us. After all, we ourselves are made of information, and if it can be erased, does that mean we too disappear completely? Our journey is only beginning. In the coming chapters, we will examine what Einstein's theory truly predicts, what quantum mechanics asserts, and how the famous black hole information paradox was born. We will meet the great minds who entered this intellectual battle and learn about the answers they proposed. And when we take the next step, you will realize that this is not only about the cosmos, but about ourselves. For in studying black holes, we are, in a sense, looking into a mirror that reflects the very limits of our understanding. Thus begins our journey, and step by step, we will uncover the story of this great mystery. Imagine the fabric of space-time, as Einstein described it. We are used to thinking of space as emptiness, and of time as the ticking of a clock. But the theory of relativity overturned these notions. Space and time form a single canvas that can bend, stretch, and compress under the influence of mass and energy. The greater the mass of an object, the stronger the curvature. Stars, planets, even we ourselves slightly bend the fabric of space-time. But if the mass becomes enormous and concentrated in a small volume, the curvature turns into a pit, a black hole. This is not just an object. It is a region where familiar laws stop working, and our imagination meets its limit. The event horizon is the boundary beyond which nothing can return. Picture a waterfall. If you are swimming down a river and approach the edge, you may still turn back. But at some point, the current becomes so strong that no force can save you from falling. For light and matter, this edge is the event horizon. Everything that crosses it disappears for the outside observer. The story of this idea's discovery is worthy of a novel. In the 1930s, the young American physicist Robert Oppenheimer, together with his student Hartland Snyder, showed that a star that exhausts its fuel does not always explode as a supernova. If its mass is large enough, it collapses under its own weight. And then a black hole is born. This result was so revolutionary that it was almost ignored for decades. The world was not yet ready to accept the existence of such objects. Think about it. For the first time, physicists seriously claimed that a star could vanish, leaving behind only emptiness into which even light cannot penetrate. Doesn't that sound like myth? And yet, it is a strict conclusion from Einstein's equations. There is no room for fantasy here, only mathematics and logic. But there is also a philosophical aspect. The event horizon is a boundary of our knowledge. We see light from matter falling into the whole. It becomes more and more red-shifted, dimmer, and finally disappears. For us, time seems to stop at the horizon, but for the falling observer, it is different. They cross the boundary and continue on. Who is right? This question stirs the imagination. It shows that reality may depend on perspective. Outside, eternal darkness. Inside, a continuation of the journey. Where is the truth? And can we even speak of a single truth in such a case? In these reflections, the first conflict arises. Relativity describes the event horizon as a clear boundary, but quantum mechanics suggests that any boundary must hold information. Here begins the tension between the two greatest theories of the 20th century. After his work on collapse, Oppenheimer turned to the atomic project, becoming known as the father of the atomic bomb. But his name is forever tied to black holes as well. Sometimes in the fates of people and in the fates of ideas, light and darkness intertwine in remarkable ways. Let me ask you, if even a star that shines for millions of years can vanish into the abyss, what does this say about our own transience? And at the same time, about the grandeur of the laws of nature that allow us to predict such destinies? We have just approached the event horizon, both literally and metaphorically. Ahead lies an even more surprising realm of science, quantum mechanics. It will bring into the picture elements of probability, uncertainty, and the mystery of information. And so we move forward. Let the river of time carry us to the next turn, where space meets quanta, and the laws themselves begin to argue. Quantum mechanics is a world that defies our common sense. Unlike Einstein's strict geometry, here uncertainty reigns. Particles can exist in several states at once, and the outcome of an experiment cannot be predicted with certainty, only probability. Think of Schrödinger's famous cat. Until we open the box, the cat is both alive and dead at the same time. This is a metaphor for how particles behave in the quantum world. They exist in a superposition of states until the observer intervenes, and it is precisely this property that makes quantum mechanics so mysterious and so fundamental. When we try to connect this theory with black holes, astonishing questions arise. If information is contained in quantum states, can it vanish when a particle falls beyond the event horizon? Or must it somehow be preserved? One of the cornerstones of quantum mechanics is the principle of conservation of information. This is not just dogma, but the result of hundreds of experiments. Quantum systems evolve in such a way that information about the initial state can always, at least in theory, be recovered. If this principle fails, the entire structure of physics collapses. Here we face a problem. Einstein says that a black hole hides everything beyond the event horizon. But quantum mechanics says information cannot disappear. How do we reconcile these two claims? History shows us that it is precisely at the boundaries of knowledge that the brightest discoveries are born. At the beginning of the 20th century, Max Planck introduced quanta of energy to explain the radiation of heated bodies. Albert Einstein applied this idea to light to explain the photoelectric effect. Niels Bohr built a model of the atom. All these steps seemed absurd at first, but they changed our understanding of the world. And now black holes have become such a boundary. Here quantum mechanics meets gravity face to face. And here arises the conflict that Hawking would later call the information paradox. But before moving on to this paradox, let us look a little deeper into the quantum picture itself. A particle is not a tiny ball, but a wave of probability. It is described by a function that tells us where it may be found and with what likelihood. When the particle interacts with something, the wave collapses, and we obtain a definite result. Imagine an ocean full of waves. Each wave is a possibility. When we throw a stone, the waves meet, overlap, reinforce, or cancel each other out. The quantum world works exactly like that. Reality arises from the interference of probabilities. This is astonishing and, at the same time, hard to accept. If information is stored in these waves, then what happens if they vanish into a black hole? This question divided the scientific community for decades, and it is here that the great intellectual drama begins, one involving the finest minds of humanity. I want you to feel the scale. We are not talking only about distant stars and mysterious objects. We are speaking of the laws that govern every atom in your body, every photon of light that reaches your eyes. Quantum mechanics is the foundation upon which our reality rests. And if its principles contradict Einstein's theory, then perhaps a revolution in our understanding of the cosmos awaits us. Sometimes it feels as though the universe is testing us. It says, "You have solved one equation, but are you ready to go further?" And on this path, we encounter paradoxes that sound like the riddles of philosophers, but are solved in the language of strict mathematics. So, we have become acquainted with quantum mechanics and its remarkable principles. We have seen that here information is a sacred value that must not disappear. And ahead lies the paradox that changed science forever, Hawking's information paradox. And now we arrive at one of the most dramatic chapters of modern physics, Hawking's information paradox. Until the 1970s, it was believed that black holes were eternal graveyards of information. Everything that fell inside disappeared from the outside world, and that was the end of the story. But Stephen Hawking, the man who forever changed our understanding of the universe, showed that the situation was far more complex. In 1974, he performed calculations that shocked the scientific world. According to quantum field theory, space is never truly empty. Even in a vacuum, life teems. Virtual particles constantly appear and annihilate in pairs. Normally, they vanish too quickly for us to notice. But at the event horizon, things are different. If one particle falls inside while the other escapes, the escaping particle can carry away energy. This is Hawking radiation. This means that black holes are not eternal. They evaporate. Slowly, almost imperceptibly, but inevitably. And when they evaporate completely, only radiation remains. But where is the information? Here lies the paradox. Hawking radiation is completely random. It carries no imprint of what fell inside. A book by Tolstoy, a star, a spacecraft, all become a chaotic stream of particles. If Hawking was right, information is truly lost. But this directly contradicts the laws of quantum mechanics. Thus began the great debate. Leonard Susskind, John Preskill, and other physicists engaged in an intellectual duel with Hawking. They argued information must be preserved, Otherwise, the entire foundation of physics collapses. Hawking, however, insisted, black holes destroy information irretrievably. Picture the scene. A gathering of physicists, one of them claiming that the very laws of nature may be broken. It sounded heretical. Yet Hawking's authority was such that his words were taken with the utmost seriousness. At stake was not merely an equation, but the fate of science itself. This debate lasted for decades. New theories and new approaches emerged. The holographic principle was proposed, the concept of black holes having hair, and the idea that information might be stored at the event horizon. But back in the 1970s, all this was still ahead. At that time, there was only shock, and the realization that at the heart of the cosmos lurked a mystery capable of upending the familiar order. Think about it. If information truly vanishes, then predictability collapses. The universe ceases to be a machine in which the future can be derived from the past. It becomes chaos, where events are irreversible and inexplicable. Are we prepared to accept such a picture? This paradox changed not only physics, but philosophy, for it raised the question, what is knowledge, if the universe itself can erase information? Does it mean that truth is relative, that it can vanish like light swallowed by a black hole? Stephen Hawking, despite his illness, waged this debate with extraordinary energy. His image, a man bound to a wheelchair, yet battling for the laws of the cosmos, became a symbol of human spirit and resilience. And in this struggle, ideas were born that would be developed for decades to come. And so we have seen how a paradox emerged at the heart of a black hole. In the next part, we will turn to the theories that sought to reconcile Hawking's vision with the principles of quantum mechanics. We will learn about holography, about horizons that might hold secrets, and about how the scientists' debate became a step toward a new picture of the universe. After the debate sparked by Hawking's ideas, physicists began searching for new ways to reconcile quantum mechanics with relativity. One of the most striking concepts to emerge was the holographic principle. It was born from reflections on how information might be stored in a black hole. In the 1990s, Dutch physicist Gerard T. Hooft and American theorist Leonard Susskind proposed an idea. All the information that falls into a black hole may not be hidden inside, but encoded on its surface, the event horizon. Just like a hologram, which contains a three-dimensional image on a flat sheet, a black hole could store three-dimensional information on its boundary. The idea was astonishing. It overturned our very conception of space and reality. It suggested that what we perceive as a three-dimensional world might actually be a projection of data written on a two-dimensional surface. The universe as a giant hologram. It sounds poetic, yet it is a serious physical hypothesis. In this context appeared the famous phrase, "Black holes have no hair." Coined by John Wheeler, it meant that a black hole is described by only three parameters: mass, electric charge, and angular momentum. Everything else is erased. But if information is erased, where does it go? The holographic principle offered an answer. It is stored at the horizon. Imagine a diary. You write down your thoughts, emotions, and experiences. Then the diary is thrown into a fire. The pages burn, the ink vanishes. But imagine that the fire somehow leaves an imprint of each page on its surface. That is how Susskind and T. Hooft envisioned black holes preserving the memory of what fell inside. This idea inspired the development of entire new fields of theoretical physics. In particular, it became the foundation for the so-called holographic duality, or ADS/CFT correspondence, proposed by Juan Maldacena. According to this hypothesis, physics in a space with gravity can be equivalent to physics on the boundary of that space, where gravity is absent. This opened entirely new horizons. Philosophically, it goes even deeper. If reality can be a hologram, does that mean our everyday lives are merely projections of something more fundamental? Could the memory of the universe itself be stored on its boundaries? These questions force us to reflect on the boundary between physics and metaphysics. But let us return to our story. The holographic principle was an answer to Hawking's challenge. It showed that information does not vanish without a trace, but simply changes form. It rises to the surface, leaving its imprint on the event horizon. Thus, quantum mechanics preserves its law of information conservation, and the universe remains coherent and logical. And yet, the story does not end here. Even with holography, questions remain. How exactly does information return when a black hole evaporates? How can Hawking's chaotic radiation carry traces of what once fell inside? These mysteries would continue to puzzle scientists for many years. We have touched upon an idea that sounds like science fiction, yet rests on solid mathematical ground. In the next chapter, we will continue this journey and explore how the event horizons themselves may hold the key to understanding the nature of information and the memory of the universe. When we speak of the event horizon as the keeper of information, a new question arises. Could the horizon itself be an active participant in the cosmic drama? For a long time, it was assumed that the event horizon was simply a boundary, a surface without properties. But new ideas suggested that things could be far more intriguing. In 2012, a group of physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, proposed a concept that shook the scientific world. It became known as the firewall paradox. According to their calculations, if information truly survives and emerges with Hawking radiation, then the event horizon cannot be smooth and calm. Instead, it must be a raging wall of energy, a kind of cosmic bonfire that destroys anything crossing the boundary. This was a shock. After all, general relativity insists that an observer crossing the event horizon would feel nothing special. For them, it would be a moment indistinguishable from any other in their journey. But quantum reasoning suggested the opposite. Instead of a gentle transition, there would be instant annihilation. The firewall paradox became a new battlefield. Some physicists saw it as the logical consequence of trying to reconcile quantum mechanics with gravity. Others argued that it was far too radical, undermining the very essence of relativity. Yet the debate revealed one thing. The event horizon is not merely an imaginary line, but a profound puzzle that may hold the key to understanding information. Picture a traveler walking through the desert. He sees a mirage, an oasis in the distance. But the closer he gets, the clearer it becomes. It is an illusion. So it is with the event horizon. We think we understand its nature, but upon closer examination, it proves to be far more complex. Perhaps the horizon is not a boundary at all, but a dynamic surface where quantum processes intertwine. This thought leads to another idea. Perhaps a black hole is like a giant quantum computer. It receives information, encodes it on its horizon, and then slowly computes, returning it in radiation? If so, then event horizons are not graves of information, but intricate processors of data. The philosophical meaning here is immense, for in that case, the universe itself is like a memory machine. Every act, every event leaves its trace, and nothing vanishes completely. Does this not remind us that our lives too are chains of traces, imprints, and stories that do not fade without leaving a mark? But this picture also has a frightening side. If the event horizon is a firewall, then it becomes a symbol of the ultimate limit of knowledge. We cannot look beyond it, because nature itself forbids it. It is like a book whose pages are sealed shut. We see the cover, but the contents remain hidden. Scientists continue to debate. Some insist that firewalls are real. Others propose new approaches that avoid such a harsh scenario. But one thing is clear. Event horizons are not just mathematical abstractions. They are the stage on which the drama of information unfolds, where quantum laws and Einstein's theory clash. In the next chapter, we will explore how these debates led to the creation of new concepts of space and time, and you will see that the very fabric of reality may be far more flexible and mysterious than we ever imagined. We have now reached a point where the very notions of space and time begin to waver under the pressure of new ideas. If event horizons can be active, if information is stored at the boundaries, then perhaps our picture of the cosmos requires a complete reconstruction. One of the boldest hypotheses of recent decades is the idea that space and time are not fundamental. They may be emergent, born from something deeper, quantum connections, known as entanglement. Quantum entanglement is a phenomenon in which particles that once interacted remain linked, even if separated by billions of kilometers. Measuring the state of one particle instantly reveals the state of the other. Einstein called it spooky action at a distance. Today we know that it is not a mystical metaphor, but a physical fact, confirmed by countless experiments. The notion that space itself may be woven from quantum entanglement sounds like poetry, but mathematics suggests it may be true. Perhaps the geometry described by relativity is merely an expression of a deeper quantum structure. In that case, space and time are not arenas of events, but derivatives of information. Imagine a fabric woven from threads. Each thread is a connection between particles. The denser the weave, the stronger the fabric. So it may be with space, a pattern created by a network of entanglement. In this picture, information becomes the very building block of the cosmos. Physicists began to suggest that gravity itself may be an expression of information. Ted Jacobson, Eric Verlinde, and others proposed theories in which the laws of gravity emerge not from geometry, but from thermodynamics and information. Gravity as an entropic force, an idea that at first seemed insane, but is now increasingly discussed in scientific circles. The philosophical meaning of this approach is profound. If space and time are not absolute entities but consequences of quantum links, then our entire understanding of reality changes. We are used to thinking that we live inside space, that we move in time. But what if these are merely languages through which the universe expresses a deeper truth? Think about it. If space is born from information, does this not mean that we ourselves are part of that informational pattern? Our thoughts, our memories, our stories, they too are information. Perhaps it is this that binds us to the cosmos at its deepest level. Against this backdrop, black holes cease to be mere astronomical objects. They become laboratories where the boldest ideas about reality are tested. Where gravity and quantum mechanics clash, new concepts of space, time, and information are born. And yet, as daring as it sounds, many questions remain. If space and time emerge from entanglement, how exactly does this process work? Can we build a complete theory that unifies these ideas? Scientists continue to search for answers. We have arrived at the threshold of a new philosophy of physics. In the next chapter, we will see how the debate over black holes has shaped our understanding of the universe as a whole. We will explore what it means to live in a reality where information is more fundamental than matter and energy. Throughout these chapters, we have spoken of black holes as laboratories where two great theories collide. But what does this mean for the universe as a whole? If information plays such a fundamental role, then perhaps cosmology itself must be reimagined. By the end of the 20th century, it became clear that our universe is expanding at an accelerating rate. This discovery, made through observations of distant supernovae, shook science to its core. The concept of dark energy emerged, a mysterious force that drives space apart. But what if the key to this mystery also lies in information? Some physicists began to see the universe as a giant information storage system. Each part of it is a kind of bit, carrying information. Then, the expansion of the cosmos can be understood as the redistribution of these bits, as the growth of entropy. Entropy is a measure of disorder, but also a measure of information. The larger the universe, the more possible states it has, the richer its library. This idea resonates with the Bekenstein principle, which states that the amount of information contained within a volume is determined by the area of its surface, not its volume. Think about how paradoxical that is. We are used to believing that a cube holds more information than a square, but physics tells us surface matters more than volume. This is a hint that our universe may be structured in a way quite different from how it appears. Philosophers see in this a challenge to conventional thinking. If reality can be described in terms of information, does that mean matter itself is merely derivative? What is more real, atoms or the information that describes them? These are questions that take our breath away. In cosmology, another important point arises. If information never vanishes, then the universe itself holds the memory of every event that has ever occurred. In a sense, the past never disappears. It is inscribed in the fabric of the cosmos. And perhaps in the future we will learn to read these traces just as archaeologists read layers of earth. Imagine that the entire history of humanity, every voice, every thought, is recorded somewhere in the structure of space. Perhaps this is why we are drawn to the stars. We feel that they carry within them the memory of ourselves. But this picture is not only inspiring, it is unsettling. If information is eternal, then mistakes are eternal too. Every action leaves a trace, and then arises the question, could the universe itself be a kind of moral chronicle where nothing is forgotten? Scientists are cautious about such conclusions, but the philosophical implications are obvious. When we speak of black holes and information, we are not only speaking of mathematics, but of the meaning of existence. For if information is the foundation of all, then our very existence takes on a new dimension. In the next chapter, we will turn our attention to how these ideas have influenced modern technology. It turns out that the study of black holes and quantum information is inspiring the creation of quantum computers, machines that may change our future. When we hear about quantum information, and the holographic principle, it may sound like pure theory, far removed from practice. But these very ideas inspired one of the greatest frontiers of modern science and technology: quantum computing. A quantum computer is a machine that operates not with bits, like our laptops and phones, but with qubits. A qubit can exist in multiple states at once, thanks to the principle of superposition. Moreover, qubits can be entangled with one another, enabling the processing of enormous amounts of information in parallel. The idea of quantum computation is directly tied to the same principles that underlie debates about black holes. If information is fundamental, then it can be stored, encoded, and transformed in new ways. Physicists studying the fate of information in black holes contributed greatly to the development of quantum information theory. Engineers then turned these ideas into the first prototypes of quantum machines. Imagine a game of chess. A classical computer checks millions of possible moves, but does so sequentially. A quantum computer can consider many combinations at once through superposition. This does not mean it thinks faster, but that its approach to information is fundamentally different. And here lies the paradox. Reflections on event horizons and information paradoxes are helping to build machines that may one day solve problems classical computers never could. Encryption, molecular modeling, optimization of complex systems, all of these may be transformed by quantum computing. Philosophers say, ideas have consequences. Black holes may be billions of light years away, yet their mysteries are already shaping our lives, even if indirectly. The science of the impossible is becoming the technology of the future. But there is another side. Quantum computers are still in their infancy. They are sensitive to noise, require ultra-low temperatures, and complex error correction. Yet the very fact that humanity is taking steps in this direction shows that we stand at the threshold of a new era. And here it is fitting to recall black holes again. Perhaps they themselves are natural quantum computers of the universe, processing data on their event horizons. In that case, our technologies are but faint reflections of cosmic processes. Think how symbolic this is. We study the abyss, and the abyss teaches us to create new forms of memory and mind. Human thought mirrors the structure of the cosmos, and in this, there is something profoundly inspiring. In the next chapter, we will turn to how debates about information in black holes have influenced not only physics and technology, but also culture. For the images of black holes have long penetrated literature, cinema, and art, becoming symbols of the limits of human knowledge and, at the same time, of infinite possibility. We have already seen how debates about information in black holes influence the development of quantum physics and technology. But no less important is the way they entered culture and human imagination. Black holes have become symbols of the limits of knowledge, of the abyss into which light and meaning disappear, and at the same time of portals to new horizons. In literature and cinema, black holes have long ceased to be mere astronomical objects. They have become metaphors for human fears and hopes. Recall the film Interstellar, where the black hole Gargantua was depicted with stunning scientific accuracy. Yet the heart of the film lies not in physics, but in the idea. Love and memory can transcend even event horizons. This is an artistic response to the very question that torments physicists. Does information truly vanish? Science fiction has always been a mirror of science. When Arthur C. Clarke wrote about stars and space, he intuitively sensed ideas that later found confirmation in research. When modern writers and directors use the image of the black hole, they are working with an archetype of the unknown, with a symbol of eternal mystery. In philosophy, black holes have become symbols of the limits of rational knowledge. Michel Serres wrote of them as points where language fails. Jacques Derrida saw in them metaphors of absence, of a void around which meaning is built. These reflections show that a black hole is not only a physical reality, but also a cultural symbol. It is fascinating that even in everyday speech we use the phrase information black hole to describe lost data or something incomprehensible. This is an example of how a scientific idea enters language and becomes part of collective consciousness. But why is it black holes in particular that so captivate our imagination? Perhaps because they unite opposites. They are ends and beginnings, death and birth, destruction and preservation. They both terrify and inspire. In them we see reflected our own longing for the unknown. And here is an important point. The deeper science studies black holes, the richer their symbolic meaning becomes. When physicists debate the fate of information, they are, without realizing it, posing a philosophical question. Can meaning vanish? Can history be erased? These questions trouble not only scientists but every person. For we too store information about ourselves, about our loved ones, about our time. The thought that this information could disappear without a trace is frightening. But if even in the cosmos information is preserved, albeit in altered form, then perhaps our memory is eternal too. Culture and science meet here at a single point. Black holes become bridges between strict equations and the human soul. They remind us that the search for truth is not only about formulas, but about meaning, and that within every scientific debate lies hidden philosophical and artistic potential. In the next chapter, we will turn our attention to how ideas about information in black holes influence our understanding of consciousness. For if information is a fundamental entity, then perhaps our mind is something more than a biological process. We have already seen how ideas about information in black holes extend beyond physics and enter culture. But there is another direction they lead, reflections on the nature of consciousness. If information is a fundamental entity, then could our very self be a form of information? Consciousness has always remained one of the greatest mysteries. Neuroscience tells us it arises from the activity of billions of neurons. Philosophers debate whether it is a product of matter or something more. But through the lens of informational theories, a new perspective emerges. Perhaps consciousness is not merely biology, but a process of processing and preserving information. Think of memory. We perceive it as a function of the brain. But what if memory is a universal property of the universe? Black holes compel us to consider exactly this. If they can retain information about everything that falls into them, then perhaps the cosmos itself is a vast memory, of which we are a part. Physicist Roger Penrose proposed bold ideas about the link between quantum processes and consciousness. His hypothesis of quantum orchestrations in the brain's microtubules remains controversial, but it shows that scientists are increasingly seeking bridges between physics and the philosophy of mind. And the paradox of black holes is one of the points where such bridges are built. Imagine this. If information is eternal, then perhaps consciousness is more than a temporary process. Perhaps it is inscribed in the fabric of the universe, just as the laws of physics are. In that case, death is not an end, but a transition of information into a new form. This thought is both frightening and inspiring. Of course, for now, these are only hypotheses, but their philosophical meaning is clear. We are informational beings. Our thoughts are codes. Our memories are records. And when we reflect on black holes, we inevitably ask ourselves, what happens to the information about us? Perhaps this is why the topic of black holes touches our hearts so deeply. It makes us reflect not only on the cosmos, but also on our own nature. Gazing into the abyss, we seek an answer to the question of what it means to be human. In this sense, the information paradox is a mirror. It reflects not only the fate of stars, but also our deepest fears and hopes. It reminds us that the question, where does information go, is at the same time the question, where do we go? In the next chapter, we will turn to how philosophers and scientists together are trying to answer these questions. We will speak of the dialogue between science and philosophy and of how they help each other approach the mystery of existence. We have reached the point where science and philosophy meet face to face. Black holes, once purely astronomical curiosities, have become arenas where the nature of knowledge, truth, and meaning is debated. For the question of whether information disappears is not only a physical one, but a philosophical one as well. Philosophers have always wrestled with the problem of identity. What makes an object itself? If a star, a person, or a civilization vanishes, does something of its essence remain? In physics, this question takes on a precise form. Can the information describing a system disappear without a trace? Here, the scientists' debate becomes part of a great philosophical dialogue. Some philosophers see black holes as proof of the limits of rationality. We can describe processes up to the event horizon, but beyond it, our knowledge ends. Others argue that the very information paradox is a challenge, calling us to expand our notions of knowledge. If science encounters a contradiction, it does not mean the world is absurd. It means our models are incomplete. Scientists, in turn, increasingly turn to philosophical categories. They speak of reality, essence, memory. They ask questions once reserved for philosophy. Could it be that space and time are merely phenomena, concealing a deeper foundation? Could information be more fundamental than matter? In this dialogue, a new culture of thought is born. Science becomes more self-aware, philosophy more open to experiment. Together they build bridges toward understanding what once seemed unreachable. It is fascinating that such dialogues have always existed. The Pythagoreans believed the world was built on numbers. Descartes sought truth in clear and distinct ideas. Kant claimed that space and time were forms of our perception. And now we return to these questions at a new level, armed with Einstein's equations and quantum mechanics. Think about it. When we discuss black holes, we are not only discussing physics, we are discussing the nature of knowledge and the limits of the human mind. We are discussing how the universe remembers and forgets. In this sense, every scientific theory becomes part of a philosophical picture. Perhaps this is why the theme of information touches us so deeply. It unites strict calculations with eternal questions of meaning. It reminds us that science is not only about answers, but about searching, and that in every experiment, in every equation, there lies a philosophical meaning. In the next and final chapter, we will bring our journey to a close. We will try to see black holes not only as physical objects, but also as symbols that open new horizons of understanding before us. We have reached the end of our journey. From the earliest hints of black holes to Hawking's paradox, From the holographic principle to reflections on consciousness and philosophy, we have traveled far, and each step has revealed new horizons before us. Black holes have ceased to be mere astronomical objects. They have become symbols of the limits of our knowledge, and at the same time doors into the unknown. They teach us that even where everything seems to vanish, new forms of being may be hidden. That information is the foundation of the world, and nothing ever truly disappears. We have asked questions that still have no final answers. What happens to information that falls into a black hole? Does it evaporate with radiation? Is it stored on the event horizon? Or perhaps the universe itself is a grand hologram, where every step and every choice we make is forever inscribed in the fabric of the cosmos? And perhaps the greatest lesson is that the search for truth is endless. Science never places the final period. Every answer gives rise to new questions, and in this lies its greatness. For it is thanks to this that we continue to move forward, to discover, to dream. Gazing into the abyss, we see not only a mystery, but also a mirror. Black holes reflect our fears and our hopes. They remind us that human beings are creatures who search for meaning even in the deepest darkness. And it is this search that makes us truly great. I want you to carry one thought from this journey. Information is eternal. It can change, take different forms, hide behind horizons, but it never disappears. And if this is true for the universe, perhaps it is true for us as well. Our actions, our thoughts, our stories, all of these are written into the cosmos. Let this thought inspire you. Let it remind you that even in the hardest of times we leave a trace, and that trace is never erased. We are part of a great story, one that continues and will continue. And so, our journey comes to an end. But at the same time, it is only beginning. For each of you now carries within you this mystery, this spark of curiosity that leads humanity to the stars. And who knows, perhaps it will be you who takes the next step in solving the riddle of black holes. Thank you for being with me on this journey. Until we meet again, in science, in dreams, in the universe.